Thanks very much for the opportunity. Well, first of all, to be here. It's lovely to be in the sunshine, having escaped the winter in England. Just yesterday, yes, I think it's yesterday, I left and arrived here. It's great to be here. I think it's 15 years since I was last here in Santa Barbara. And this bit's the same, and the ocean's still there. There's a few more buildings around than last time I was here. So it's a pleasure to be here and talk to you a little bit about some of problems that I've been interested in recently. And I hope that chimes with some of the things that people might be interested in on the inflation program, but may be of general interest as well. I'll try and keep it accessible, I hope. I'm sure you'll please do ask if you've got questions about what I'm saying as I go along. So this is some work I've been doing to understand well, I'm interested in inflation because I'm interested in it really as a model for the origin of structure in the universe. This work, I should say, it's with my PhD student Chris Patterson, who's just finishing and looking for a postdoc job currently. Vincent Vanine, who was a postdoc with us in Portsmouth, is now faculty in Paris. And our collaborators. This was motivated particularly by trying to understand some of the formation of extreme objects in the universe. So the standard approach to extreme fluctuations in the density field, the standard approach to describing density perturbations is that they originate from quantum fluctuations and inflation and in accelerated expansion in the very early universe provides us with a nice model in which to understand why quantum fluctuations on the microscopic scales should be give us an origin for structure on the very large scales. And usually we do that in a perturbative way. But here, really, we are looking for a non-perturbative description. So it's a non-perturbative approach to studying, and you want to use that to study large fluctuations, or indeed rare excursions in the density field. And it's what I'm talking about really is the primordial density field. So, by which I mean in the radiation era, at the beginning of the hot Big Bang, standard hot Big Bang model, so we're setting up the distribution of matter in the radiation and subsequent matter-dominated eras. Okay, and this was specifically motivated by people's interest recently in studying, renewed interest in studying primordial black holes, and whether these can be produced in some models of inflation. So, and they're the archetypal sort of example of rare fluctuations. You don't want too many of them, or else they'll form cold, dark matter, but dominating in the very early universe, early on, too early in the history of the universe. But there's a sort of fascination with these objects since they were first discussed by Stephen Hawking in the 70s. And especially today, as people worry about whether there's any particles out there beyond the standards, the particles of the standard model. We need cold dark matter in cosmology, indeed for the process of structure formation. And the one way you might perhaps do it with the standard model particles is if you can collapse them into black holes. So they very weakly, only gravitationally interacting particles, effectively particles. But to form them during inflation, you need large density contrasts. So they could form in the very early radiation-dominated universe. Density perturbations, and I'm going to characterize those in terms of the quantity zeta, which I'll define later. And these can form when they exceed a critical value. And people study what that might be, but it's when the metric perturbations are of order unity, as modes come inside the horizon at the Hubble scale in the radiation era. And to calculate the abundance of these objects, what people typically do is they look at the distribution of the primordial density perturbation. So you've got a distribution, and you have a probability distribution for zeta. And in the standard model, that would be a Gaussian, which I've tried to draw there. And you're really interested in the fraction that exceeds some critical value. So you're integrating up above some critical value of order unity there. And the standard approach is to describe the perturbations originating from, say, free field fluctuations during inflation. And on large scales, that gives you effectively a Gaussian distribution if you're just using the linear theory. And although people study deviations from non-Gaussianity, the language of studying those deviations really is through studying skewness or kurtosis. So they're interested in distorting this shape by some asymmetry, perhaps some skewness or some kurtosis, that flattens the distribution. But these are all based, basically, the standard approach is a Gaussian or a sort of polynomial modification of that Gaussian. So it's a Gaussian or a modified Gaussian distribution. And you might wonder whether that's really a good way of describing the tail of the distribution. These are good descriptions of typical fluctuations, but all of these are sensitive to whether the distribution is really close to a Gaussian in these extreme values. And what I'll argue today is that typically the tail is not a Gaussian.
What time is this again, eventually?
So, primordial, I really mean form in the radiation era. But the seeds for this, so the curvature, the dimension of density perturbation zeta is produced during inflation. So you get these large, you could have these large fluctuations in the metric, but during inflation they're getting pushed out to very large scales. So the gradients are not large until the modes come back inside the horizon, and then it's at that stage, and you come back in during the radiation era, and so that's when they form. Okay, so that's the motivation. Generally, it's just also a nice interplay between classical and quantum physics here. Well, perhaps it's inevitable, right? We're studying gravitational effects, gravitational expansion of the universe, but we want to include quantum fluctuations. So, just maybe to define my terminology, at least, I was going to just define some quantities I'm going to work with say, in classical inflation. So that basically classical here, I'm also going to mean the homogeneous and isotropic background cosmology. So I'm using classical general relativity, an FRW metric. So it has a scale factor, A of t, Hubble rate. It's just the rate of change of that. But in fact, having said A of t, what I want to do is increasingly I'll tend to talk about the logarithm of the scale, so the logarithmic expansion n. So I'll be talking about the expansion in terms of n. Inflation. Specifically, I would define as any period where, in the expansion, where the scale factor is accelerating, and that means you can define a parameter epsilon, which is the rate of change of the Hubble rate, the dimensionless rate of change of the Hubble rate, and for inflation this has to be less than 1. It's always positive, it's less than 1 for inflation. But indeed I'll talk about slow roll inflation, which implies I'm talking about epsilon much less than 1, so quasi de Sitter expansion. And I'm going to just talk about a simple model of inflation driven by a canonical scalar field. So then this Hubble expansion is basically given by, I'll put the coefficients in, it's given by the potential energy of the field and the kinetic energy of the field. So we have a simple classical picture of the evolution of the field. As it classically would evolve down the potential. And slow roll here simply means that would mean that V is, the potential energy is much bigger than the kinetic energy, and that can be achieved by, in particular, at a large Hubble expansion rate. Sorry? Oh, yeah, how about I'm being conventional at this point. The slow roll inflation, the potential is much larger than the kinetic energy. Okay, and then this quantity n here, if you've got slow roll evolution of the field, you've got a large sufficient Hubble damping that the kinetic energy stays much less than the potential energy. We can define the expansion, so the log of the expansion and the integral of the Hubble rate over time, and down this slow roll solution you can replace the time evolution simply with the evolution down from one value of the field to the next. So this integral you can turn into an integral over the field values, and phi dot squared over h squared is basically, from the equations, turns out is basically the slow roll parameter. So, well, I'll start dropping the numerical coefficients, but this is basically given by 1 over the slow roll parameter, the integral over the scalar field in Planck units. So you can get sufficient inflation either with basically either delta phi can be bigger than the Planck scale, or sufficient inflation might be n bigger than about 70. And that's simply given by So e to the 70 is the ratio between the size of our observable universe, all the scales we can see as the large-scale structure in our universe today, compared to the Hubble scale at the end of inflation. So for that to be bigger than about e to the 70, then either you require phi bigger than m Planck, or indeed epsilon, well, much less than 1, crudely. Right? And that's the classical picture of how you can expand the universe with a slow rolling scalar field. But what makes it interesting, and it may be interesting that it produces a large isotropic universe, but the fascinating thing to me is that it also throws in fluctuations about unevenness about that background, because and it doesn't have to be there in the classical theory, but if this is a quantum field, then you've got quantum fluctuations on microscopic scales, and those quantum fluctuations perturb this smooth homogeneous isotropic expansion. So it's the quantum fluctuations that allow us to become a prediction of the model, and allow us indeed to test the model against the data. And the data will be the perturbations, the fluctuations in the density. So during inflation, we're basically going to move from talking about this homogeneous phi of t to effectively we keep this sort of classical background phi of t. So the standard approach would be to split that up into a homogeneous background and a perturbation, but that which varies in space and time on that background, and in particular on small scales, and that here really means scales smaller than the Hubble length. Delta phi is described by is basically you get just in the linear theory you've just got the free oscillations of the field, which you can quantize. So you've got basically you've got a quantum oscillator. But in the expanding background, so sub-Hubble, by the way, talk about wave numbers, that would be wave numbers bigger than the co-moving Hubble scale. Whereas on large, but the expansion connects those to the large scales, transmit those to the large scale field. So super Hubble. And then you've got, well, in the quantum theory, you've got a squeezed state. These oscillations, you've got a single growing mode, and that means it's well described by effectively classical perturbations of the field, a classical random field. And that's where, at first order, you've got a field obeying, a free field obeying Gaussian statistics, and you can start putting in the interaction terms perturbatively to study the 3-point and 4-point function derived from that. And I suppose the only thing I want to write there is the sort of famous sort of result for the, if you've got a weakly coupled field in a quasi-de Sitter expansion, then sort of typical amplitude of fluctuations. So you can put in corrections from interactions and from say the gravitational, first order gravitational coupling, but the fluctuations of the field as they transition from sub to super horizon scales is basically given by the Hubble rate. So fluctiations over 2 pi squared.
I have a question. So this process of classicalization, is it just simply because of the expansion, or is the, as you said, the interactions are crucial? Like if you have a free field, for example.
Yeah. So all I'm talking about here is just from the free field theory. So yeah, it just goes into a squeezed state. So if you had information about the decaying mode full field, it's still a in this description, still a quantum field, but because it goes into the squeezed state, you basically, the properties are described just by the growing mode, and therefore you can't see. So people have looked to see if you to measure, and if there's anything left to measure, but basically unless you can find information about the decaying mode of the state, it looks just like a classical field. So I don't think anyone has found an observable. You could go and see that this is truly quantum in origin. But so yeah, and that's going to allow me, or I'm going to use that as justification for indeed treating these fluctuations that come from the quantum field as basically a classical random field. So that's the sort of starting point really for stochastic inflation, is indeed to fold that into the evolution, what would looks like the classical evolution of the field in the large scale regime. Okay. So the final step in the sort of standard picture here is important step is to connect the field fluctuations to the density perturbations, indeed so I keep talking about primordial, so the radiation era, say, density perturbation. And that, I mentioned back across there, is defined really. I'm going to characterize with this quantity zeta, and it's dimensionless density perturbation we'll work with is simplest really to think of in terms of the perturbation in the metric, in the sort of local scale factor that comes from a perturbation in the expansion caused by these field fluctuations during inflation. But the picture, I'll try and draw for you, is that you can think of the field fluctuations. So this is time or expansion in different parts of the universe, where on some initial flat geometrical hypersurface, constant time during inflation, you've got field fluctuations, a bit more or a bit less, fluctuations in the quantum field here, and that affects the subsequent expansion history. And in particular, what this delta n here is measuring is the fluctuation in the expansion history to reach a uniform density hypersurface. And that's a useful definition because we can construct that during inflation, but we can also construct it after inflation. And the useful aspect of this, first pointed out by Jim Bardeen in the 80s, was that this quantity here is constant for adiabatic density perturbations on super Hubble scales. And that kind of is exactly what we want in, say, single field inflation models to make a prediction from when a mode crosses outside the horizon to coming back inside the horizon. So during inflation, in particular when modes cross the Hubble scale during inflation, you can think of zeta as being So delta n is basically, you can think of as being h delta t, time perturbation along the evolution, and so that would be basically delta minus delta phi over phi dot. And that sort of neatly encapsulates, so the delta phi here is really delta phi quantum versus phi dot, so delta phi quantum divided by phi dot times the Hubble time, h to the minus 1. So this is kind of delta phi quantum versus delta phi classical. So zeta is also precise in telling you about the sort of the different the contribution to the of the quantum evolution versus the quantum fluctuation versus the classical fluctuation along the classical trajectory. So cases where zeta reaches the critical value 1 do indeed, would flag up that you should be taking the quantum fluctuations are significant, they're non-perturbative potentially compared to the classical evolution. They're no longer just a small fluctuation on the background. Of course, well, indeed, let's say after inflation, what we see is quantities like zeta which we can relate to the density fluctuation after inflation, say in radiation or matter. So in fact, say for density, this would be a third delta rho over rho in a suitable gauge. And you can see that, e.g., the temperature fluctuations in the CMB on large scales are basically 1/5, it's minus a fifth zeta on large scales from the Sachs-Wolf effect. Okay, so, and as I say, for descriptions of the CMB, modeling large-scale structure, this is, we basically use the power spectrum, this Gaussian description here. So I was going to now sort of go beyond this perturbative description. And I would argue we can do that through this, what we call the stochastic inflation approach, where really we're using the same machinery, but a different interpretation, really, a different split here on how we incorporate those quantum fluctuations. Instead of leaving a fixed classical background, so beautifully clear when I came in, almost. We make a subtly different treatment of the fluctuations in the large-scale regime. So really this is the approach to studying the dynamics of inflation pioneered by Starobinsky, Vilenkin, Linde and others, where we'll take what was 5t in the classical model and we split it into a long and a short wavelength part. So both of these now vary in space, but and the transition between the two is basically just is given by a coarse graining scale. So you introduce a coarse graining scale. So basically some wavelength k, which is typically you take it as a constant times the co-moving Hubble scale. So sigma here should really be less than 1, so that the long wavelength modes have really gone into this squeeze state outside the horizon. And basically the long wavelength modes, or the long wavelength field now, we treat using a leading order in a gradient expansion. But that effectively means we can use locally use the FRW evolution. So we're really studying this long wavelength field. In a regime where we neglect spatial gradients, the evolution is really, we can think of this as simply being phi of t at each location, each different patch with a coordinate x. So they follow the local Friedmann-Robertson-Walker equations, except that we have this the quantum fluctuations continually transitioning from the short wavelength, from the sub-Hubble scale to the super-Hubble regime. So you have a stochastic noise term in the evolution equations. So, well, if I cut to writing down what so we basically have a Langevin equation for the evolution of this long wavelength field. So if I write it as evolution with respect to the expansion of the field phi, the classical slow roll equations basically tell you it's driven by the gradient of the field, damped by the local expansion rate. But now we need to add in this noise term, zeta psi phi here, and if it helps, you should think of that as having an sort of typical amplitude given by the local expansion rate h. And so this is a sort of unit amplitude Gaussian noise term. And that's been studied in terms of many years in terms of trying to understand and model the evolution of the fields with respect to time in this expanding universe. So you can rewrite this as a Fokker-Planck equation. And this would be for probability distribution of the, and so this is would be set up for the probability distribution for the field or fields as a function of time, which here I'm going to be using the expansion n as the variable there. So basically you end up with an equation where dp by dn here is given by a differential operator which includes a term from the quantum diffusion term as well as the classical drift term. So this is basically in the Langevin equation you've got the classical drift and a quantum diffusion term. And so schematically you get this evolution of the fields as a function of the expansion. Yeah.
What's the status of deriving this as a systematic approximation?
So so from here to here, it's just maths, I think, to to rewrite the probability distribution, but you're asking about using this as a description of
Going
the
from
real.
full quantum description to this.
Yeah.
So I've spent a huge amount of time on that from 1991, and
Okay, so what's the step?
so I have a new framework to try and deal with stochastics. We're very interested in the nonlinear terms, but you can write down the full Einstein equations. Then there's a interesting approximation where you drop grad phi type terms, but you keep Laplacian phis. That gives you a unified framework, which is not fully self-consistent, of dealing with the coarse-grained and the fine-grained at the same time. Then you do a bipartite split, which is what's happening here between the coarse and the fine, and you systematically look in detail at the nature of the fine. And in order for the term that appears to be useful, you have to be very careful about the hypersurfaces you are doing the communication of the fine grain to coarse grain on. And so there is a preferred hypersurface, which is uniform Hubble times the expansion factor, because that's the analog of wave number. And so if you do that, you can make the stochastic fluctuation term be the most Gaussian you can get. Otherwise, the time hypersurface of the split between coarse grain and fine grain builds in non-Gaussianity. And so, and that's not the sort of non-Gaussianity you want. That's a controlled non-Gaussianity. Anyway, so that's sort of state of the art. And then the interesting issue is, were you justified in knocking out grad phi terms? And there are certain circumstances where that can't be done. And so we're keen about that.
Yeah. So I think, so there's lots of work being done on that, and I think as far as you can, you show that it's been shown this is a good description of things that can be tested, but so for example, you can test it against that perturbative approach. So that's or you can try and construct this sort of gradient expansion.
We never published, but we've gone quite a distance beyond that, and we're doing a joint relations and numerics. So the other interesting way of trying to look at this is to not deal with Fokker-Planck as a description, but to try and deal with evolution in a sequence of coherent states, which is about the closest that you can get to classical representations. And so that's actually one of the best representations for the coarse-grained structure. And so there's a really interesting analog of trying to use coarse-grained and fine-grained coherent states to do a step, which is the kick step, which is the stochastic step, and then the drift step, which is the long wavelength evolution. And it's very similar to a path integral approach. So there's a framework, but then the devil is in the details of how you do higher order quantum corrections to it. And that is still something being explored by, and it's not easy.
There's a recent paper by Gorbenko and Senatore where
I wanted to ask about it also. Yeah.
What?
I wanted to ask exactly the same. No, go ahead. I'm just.
Where they claim to give a derivation of this for the case of field in de Sitter space. So like a 5-4 in de Sitter.
Which paper are you referring to?
Gorbenko and Senatore.
Oh, that one. Yeah, okay. That's yeah, okay.
So people have worked it through. Certainly, people have studied this in the perturbative approach, typically where you're basically doing the field theory on the classical background and show that you can reproduce the terms that are here. But of course, potentially what you can do here is go beyond that perturbative approach. So the reason I'm using the statement non-perturbative there is simply because the background equations we're using are the nonlinear GR equations on the large scale evolution. But the traditional, they're often have to be checked against field theory type calculations. including those.
As far as I know, there are two issues. One is including gravity. That's basically what Dick has explained. And this Golbenko and Senatore paper is forgetting about gravity and talking about the scalar field theory in a fixed background. And even if it is not Gaussian, basically we can formally do stochastic interpretation. But as far as I understand, there is some still issue about when we can interpret as like stochastic interpretation, and in that case we have to ensure the positivity for the probability distribution. And those things are, as far as I understand, it's not very clear when we can ensure those.
And I'm simply going to put in. So in my analysis here, I'm simply going to treat this as a Gaussian kick for these long wave.
The general phenomenology of the communication of fine grain and coarse grain and other terms, it can all be treated as essentially what is in effect stochastic forces, but it may not be as simple as Marco.
And so the complication or the subtlety I want to introduce is to recast this now from this stochastic distribution or probability distribution for the fields into a distribution for n, so that I can study precisely the statistics of the distribution in the expansion given some initial field value. So that's a recasting of this here. So first of all, so this is basically what I'm going to call the stochastic delta n approach, and this is introduced. Well, there's a number of papers studying this in the 2010s. Enquist, Fujita, and collaborators, but the particular approach I'm going to adopt here is from Vanin and Starobinsky in 2015, where they basically recast this in terms of to invert this Fokker-Planck equation to give you a probability distribution as I say, it's for the number of e-folds given some initial field value phi, moving towards, in this case basically heading towards a surface, an end of inflation hypersurface, which we'll identify with the uniform density hypersurface, but characterized by a fixed value of the scalar field at the end of inflation. And now this obeys evolution equation, where you basically have the adjoint of that Fokker-Planck operator acting on P of phi to get the properties of the probability distribution of the number of e-folds here. And to do this, actually, there are subtleties about the hypersurfaces on which you're using to evolve the fields here. So here we were implicitly using the expansion, uniform expansion hypersurfaces and the fluctuations of the field on that hypersurface. So there's a sort of implicitly a gauge choice there, which needs to be consistent. So this is the problem we're trying to solve, and by solving this, we're then going to this enables us, it's this stochastic treatment of the expansion history that allows us to calculate the moments of the distribution for n. So of course you can calculate the average number of e-folds, and in particular of course you can calculate the statistics of the fluctuations, such as the 2-point function, in terms of the statistics of the moments of n. etc. And of course, if we were doing that just through moments of the distribution, we'd be back to the perturbative approach here. So what we did in the work with Chris Pattinson was to see how this modulate, to use this to calculate, I've rubbed this out now, but the full probability distribution function in order to calculate the abundance of, for instance, primordial black holes produced from inflation by probing the tail of the distribution. But to get to the tail, we don't really want to know about the expanding moments of the distribution order by order. We really want to get the full PDF. So in our paper in 2017, we introduced a characteristic function. So a function of a dummy variable t and the field value, which is basically the expectation of all the moments, so IT of the expansion n from a given value of the field phi. And then, if you think about what that is, the expectation of e to the it n of phi is basically integrating over all the possible number of e-folds of e to the it n of phi with some weight given by the probability distribution of n from the value of phi. So you're basically doing the Fourier transform. So if we can just invert the Fourier transform here, then we get back to the full probability distribution. And this characteristic function obeys a simple differential equation. It's basically this adjoint Fokker-Planck operator plus it acting on this characteristic function is 0. And so this is the prescription to get the full probability distribution for the expansion history, and therefore if we identify the density perturbations with the fluctuations in the expansion n, this gives us a non-perturbative description of the density field after inflation. And, well, I could go through the example that we did that for. We were doing that for basically a model of inflation where we sort of had a plateau region where we could identify a region where you went from a predominantly classical drift regime into a plateau which is the quantum diffusion dominated regime. And that's fine. And we're studying basically the fluctuations in this expansion history that come where you really consider the full quantum diffusion here. In this case, at the end of inflation. And so we construct a solution here, and generally what we found was that the result we get, at least in the limiting case, if I just take the limit where for large fluctuations in the number of e-folds, we get some dependence on the value of the field, as you'd expect. So delta phi is basically the width of this plateau regime. but there's this exponential tail, which is, okay, I'll put back in the numbers here, but it's a function of just this. It's basically an exponential decay, but not a Gaussian, just a simple exponential decay of the field here. There's basically just one parameter here, mu, which is basically the width of this plateau divided by its height. That is basically comes out as this width of the in-field relative to the Hubble rate, which is the size of the diffusion steps here. And so this is a prescription we evaluated for this, and the plateau was basically the region in which we could neglect the classical drift in order to get the solution I've demonstrated here. But recently there's a paper by Esquiaga, Garcia Bellido, and Venin, at the end of last year, and they basically go through how to do this analysis in general, and argue that in general you will find a characteristic function which has a series of poles along the imaginary axis plus some regular function. But when you do the inverse Fourier transform through an integral in the complex plane, you generally get a distribution function where the number of e-folds at late times has this general form where you're dominated by the lowest value of lambda, the lowest pole on the imaginary axis closest to the origin. And although the amplitude of that probability distribution depends on the initial value of the field, typically it has a decay rate that's independent of the field value. So it's just the decay lambda, decay rate lambda naught. So this is so should caution this is in the large n limit, but eventually for large fluctuations you'll be dominated by the lowest pole here, and the decay here is independent of the value of the field. And the argument there is that there's always a tail where when you have spent a long time in this quantum diffusion regime, you lose the memory of of the initial value of the field as you came into that regime. And I think what you're seeing here is just the decay of the probability distribution as this diffusion as you've got basically an absorbing boundary condition at the end of inflation, and you've just got this generic decay here. But nonetheless, it's an exponential tail here. So the claim is that quite generally, when you use this sort of stochastic approach, you'll find these exponential tails quite different from the Gaussian assumption that's being used, and you basically can't model them by the polynomial modifications of a Gaussian will not reproduce this exponential tail.
Could one compute? Could one compute this characteristic function, this expectation value, by you take the in classical solution, but that gives sort of like a kick. So that this is n is like the position, and e to the int like the momentum of the field. So you say that the discontinuity of the momentum should be t, and then you evaluate that by using this classical solution. Is that not reasonable?
It might be. I didn't follow all the steps though. Sorry. So
Well, if you were inserting one, you would do a classical solution which goes up and down, and it's continuous at the tip, both for the momentum and the position. But the exponential puts a discontinuity in the momentum. Then one finds a classical solution with that discontinuity in the momentum at that time, and evaluates the classical action.
I'm not sure I followed, but I'm happy. It'd be interested to discuss later if you're saying, So this is a technique, of course, to find that full distribution, and from the form of the differential equation here, these guys argue you can find the pole. In general, the poles will lie along the imaginary axis, and therefore you will have this asymptotic form here. But I think it's also the general understanding of why you should get these exponential terms.
Kind of look more or less in the asymptotic limit.
Yes.
And so the solution that it actually goes to is basically the Gibbons-Auckland entropy, which follows from the stochastic equations. And so the form, in some instances it would take that form, but it's sort of a little more general because it involves some integrals in order to determine exactly what that term is. This kind of term has been written down from time immemorial, but if you do it exactly, you get it to be, even with all of the coefficients, exactly Gibbons-Auckland, which is not surprising. It's a probability distribution.
Yeah. So, well, I'd be interested. That's right. To see how that relates to how. Yeah. So it's a simple problem in many ways, which in different ways has been studied many times before. I think the novelty here is really the idea that you can use this to describe the extreme fluctuations of the density field. But I know that's
the simplification of the problem that I like is that it's a purely conserved transport equation, except that there are two velocity terms. One's basically a classical velocity, and the other one is a diffusion velocity, and the diffusion velocity is related to a diffusion coefficient times the gradient of the entropy. And so that's a classic thing in any diffusion problem. And so it's when those two things equal zero, that is to say that you have the effectively drift upward from the V diffusion and the drift downward from V classical, when they're equal, that's sort of defining this characteristic boundary, and then you can get the behavior around it using that.
Yeah. So it's not equilibrium, but it is drifting down towards constantly drifting towards the end of inflation.
Two currents, one's going one way, the other one's going the other way, and they're trying to do balance.
But with absorbing boundary conditions, so it's losing probability. So regions of the universe here are ending inflation at one end of the well. Is maybe a slightly different
you usually
context.
can't deal with the so-called boundary because that's eternal inflation.
Yes, so it's also sensitive to the high energy cutoff. And here I'm actually assuming you'll get different forms. We've got a reflective boundary at the large cutoff, a UV cutoff here. But it is sensitive to those choices, So,
could you just summarize what?
Yes.
I didn't mean that ending. Right?
Well, I took the hint that I could summarize too. But
Could you just summarize what part of the choices that you had to be made here are important for the observations and what they do to the observations?
So,
A large-scale structure, the CMP, etc.
So, I don't think so. That's good. So to summarize, I don't think this is changing the standard approach, the results for large-scale structure. That's consistent with, because there, I should have emphasized, right, well, zeta is observed in the large, as you observe it in the typical fluctuations in the CMB are 10 to the minus 5. Right. So you're close to the peak of the distribution, you don't expect to be into this regime for those typical fluctuations. So
Why are we
it would be. So you'd be interested in these cases where you're looking for large or rare fluctuations. So primordial black holes, are where the zeta gets up to order unity would be the classic example. But I think it's also interesting to consider whether there's other astrophysical cases where you're interested in rare fluctuations, not typical fluctuations. So if you're looking at the first objects to collapse at high redshift, or the most massive clusters at a given redshift, that might be described by the tail of the distribution, not by the peak of the distribution. So I think that's why it's useful to have this different approach to studying the fluctuations. So it's consistent with the usual results for CMB and large-scale structure, but you can go beyond that into these cases. So that's was what I was going to conclude in terms of why I think it's interesting to look forward. What you see is that you might not expect the standard perturbative approach to be a good description in that regime. Of course, it's a question as to how far, whether you've reached into the tail of the distribution yet. And so that's one. So those are the sort of open questions. There's also issues like I've assumed slow roll here. So the work we're doing currently is to look at the general two-dimensional phase space, because actually these models with large fluctuations, you often violate slow roll in order to get into the regime of large fluctuations. So this may not be enough to do that. But I think the general property will remain, because the statement that you get this sort of exponential tail independent of the initial conditions means that probably you don't care necessarily which trajectory you're on in the phase plane and classical phase plane, because ultimately the tail is determined by the quantum diffusion in the potential. Yeah.
Thank you.
Yeah. So I think that's my general summary to finish there as well. Thank you.
What about primordial black holes?
Yeah. Sorry. Sorry. Well, what about primordial black holes? If you're interested in constraining models by the abundance of primordial black holes, at some level, the details. So what we find is, from this you can get a result which constrains, for example, this parameter mu is constrained by the abundance of primordial black holes. And dimensionally, you basically get a result which is very similar to the sort of slow roll perturbative results. And it's kind of by dimensional analysis, you're probably always going to get the same sort of result. And then when you, and because you're in either case you have this sort of tail of the distribution, so you're so sensitive to the parameter choice, it doesn't really change very much the shape of the potential you're allowed. If you wanted to get the right abundance of primordial black holes to be the dark matter, this, I would argue, is the way to do the calculation. But it's a fine detail really on the shape of the potential, the constraints that it gives you, and it doesn't change the fact that these models. There's a talk tomorrow, is it, about constraints on primordial black hole abundance? So in terms of the astrophysical constraints, I've of course not commented on that. To get the right abundance, you have to have remarkable fine-tuning, apparently, of the parameters. I know no natural reason to get just the right abundance, but if you want to produce dark matter from the standard model, this is perhaps the only way.
Other question?
So this statement about the tails and then decaying exponentially, how generic is the statement concerning if you change the potential, etc.? So
yeah, so
is it like you checked in a few examples, or do you have some intuition that's more generally? Or?
So we were looking at a very simple example of a flat potential in this regime. These guys generalized that we're looking at sort of linear and inflection point potentials. But the argument is that generally it will be of this form. The decay rate depends on the shape of the potential. So
so you don't necessarily need a classical potential. So if you just have the top of the potential, it's pretty like a new equation or topological equation, but still, or anything. So
I think, well, yes. So the argument is general. I think that's right. If it's this setup where you basically have an absorbing, you're looking at the fluctuations to get to this absorbing boundary condition, and the tail is always dominated by this diffusion.
Any other questions?